Give me one moment. Let me get some water. Okay, let's get started. So, everyone good so far? So today we have a lot to go over because I realized the homework covers factor groups and we didn't even go over isomorphisms. So yeah, let's do that. Okay, so share screen. Okay. So before that, just let me say the quiz starts today, right? It lasts until I think Saturday night. The quiz is on cosets, yeah. So nothing about like, you know, normal groups, right? But just cosets. So left, right cosets. There's 3 questions on it. So okay. Now let's start. So we have there's a notion of isomorphism. So this is sort of identifies which groups are like the same. So quote, let's see what we mean by the same, right? So it's, you think of it as a bijective map. So not only that, right? If it's just bijective, you could send, if the groups are the same order, you could send like element A1 to B5 and then A2 to B4, and then like, there has to be some structure, right? So it's a bijective map that preserves, I'll say preserves group operation. Yeah. So an isomorphism between 2 groups, so isomorphism between 2 groups G and G prime. It's a map phi from G to G prime. So it's bijective, and phi of G1, G2 is phi of G1. So this is the preserved group operation, right? So let's be careful here, yeah? So if I write, so I'm skipping something, but let me just write it for that, right? If this operation is star and this operation is circle, we mean phi of G1, because G1, G2 lie in the domain, right? So it makes sense that the operation is star, but here, right, phi of G1 lies in the group G prime, right? So when I write this, we mean the operation in G prime. Yeah. So everyone clear so far? Good. Okay. So question, where must identity go using this group property? What's phi of the identity? I'll write like this, e.g. the identity on G. Where must this go? So if you had to guess, right, like out of all elements in G prime. Yeah, where must the identity on G go? You know, you really don't have much of a choice since I didn't tell you what G prime is. What's like the one element you know G prime has, I guess. Go back to, so any ideas? So let's see. So if I take G and G, yeah, like not identity, then phi of G is phi of G star E, right? Because I'm just rewriting what G is because G times identity is still G. Now this must be phi of G, phi of E, right? By, you know, if phi was an isomorphism, then this must hold, right? So phi of G is phi of G, phi of E. So you see, EG. So you see phi of EG has to be EG prime, right? I mean, for these two to be equal. So an isomorphism must map identity to identity in particular, right? So it's forced by this law. Everyone clear so far? Okay. So let's do an example. So this is in the book. It's pretty easy to understand. So let's just do it. So you have R plus to R. Basically, this is positive real numbers, right? And then under multiplication, right? So again, this is without zero, right? Because there's no multiplicative inverse for zero. You can't multiply zero and get one somehow, right? Because the identity on the right hand side is one. And the map is x goes to e to the x. So this is certainly, so let's check it's isomorphism. Check phi is isomorphism. So it's certainly bijective, right? So surjective. How do you check it's surjective? Well, given A, this is math 2b, A, I don't want to use it, I don't know, given R a positive real number, what maps to R? Well, ln R maps to R, right? Because ln of R is gets mapped to e to the ln R, and that's just R. Yeah, so it's certainly surjective, and injectivity is also math 2b, right? Because if e to the x equals e to the y, then you ln both sides, you know, ln e to the x equals ln e to the y. And then this is just, you know, x equals y, right? So it's injective. And let's check that, you know, again, let me say this for all G1, G2, and G, right? So let x, y be in R. Then I need to check phi of x. So in this case, it's phi of xy, but my operation is plus, right? So it's phi of x plus y, right? I need to check that this is phi of x times phi of y, right? Because the operation on the image is multiply. So what's phi of x plus y? Well, phi of x plus y is e to the x plus y, right? From this map, x plus y maps, and then this is just property of exponents, right? And what's e to the x? Well, that's just phi of x. And what's e to the y? That's just phi of y. Yeah. So we checked all three properties. So phi is isomorphism. Everyone good so far? So nothing too hard. So now any cyclic group, let's call it G, and it's generated by A of order n. I didn't write this. So the notation, so let me just write notation. Most books use this, yeah, for isomorphism. So is isomorphic to Z mod NZ. Now, why is that? So what is our map, yeah? So Z mod NZ, and then we map to G equals A, right? So A is a generator, yeah. So order of A is n. So how do we map it? Well, we map the element K, to A to the K. So this is certainly surjective, right? Because let G be in G, then by definition, G is A to some power J, yeah? So phi of J equals A to the J, yeah? It's certainly surjective. You'll have to check well-defined, by yourself. I'll let you do that. So what I mean by well-defined is, here, right, the class of 1 and the class of n plus 1 are like the same, yeah, right? So you need to check that 1 and the class of n plus 1 map to the same thing, right? It shouldn't depend on what representative you choose. So for example, like Z mod 4Z, in Z mod 4Z, the number 1 and the number 5 are the same, right? Because mod, when you divide by 4, they have the same remainder. So you get to check those map to the same thing. Yeah. So I'll leave check well-defined. So this is surjective. Right, we proved that. Well-defined, I'll leave it to you for practice. Leave. So whenever you quotient off by something, you always need to check well-definedness. And then injectivity. This is a bit harder. So recall we had that theorem, right? If order of A is n and A to some power k is e, then n divides k, right? Hopefully you all remember that. So that's what we're going to use, right? So suppose a to the k equals a to the j, right? We need to show injectivity, right? So we need to show k is equal to j in Z mod NZ, right? So then, without loss of generality, a to the k minus j is e, right? Multiplied by a to the negative j on both sides. So then we have n divides k minus j. So without loss of generality, right? It could also be j minus k, but that doesn't matter. So using the result here, I get n divides k minus j. But what does that mean? Well, if n divides k minus j is congruent to 0 mod n, right? I mean, if you're divisible by n, you have remainder 0, right? So k is congruent to j mod n. And this exactly means that k equals j in Z mod nc, right? So it's injective. And then surjectivity is easy, right? Because phi of, so here in Z mod NZ, my operation is addition, right? So phi is exactly the same as the thing above. K plus J is A to the K plus J, which is A to the K, A to the J, which is phi of K, phi of J, right? So that part's easy. Injectivity, I guess, is the hardest in this case. Everyone clear? So if you have a cyclic group of order n, you're isomorphic to Z mod NZ. They're pretty much the same group. Yeah. Everyone clear? Or both of you clear? Is this recording? Oh yeah, it is. Okay. Okay, let's move on. So we have something called the exterior direct product. Right, so given two groups, make a bigger group. Right, so if I have G under dot, that's my operation, and H under circle, right? Then we make a group called G cross H is just the Cartesian product. So this S sets, and we define operation component-wise. Yeah, so G1, H1, G2, H2, by definition, we define the operation to be, we do everything component-wise. So G1 dot G2 and H1 circle H2. I mean, this is, probably obvious, right? Or probably the only way you can make a group. It turns out you can do something else, but this seems like the most obvious choice, right? You just do everything component-wise. And then same for more than one product, right? So everything is still component-wise. So you could do the same for a finite number of products. And question, what's the order of G, and H? Or if you like, I'll write it like this. Right, if you need both of them to be identity, right? Because the identity for this group, right? Identity is EG and EH, right? So normally I write E for identity, but here you need to specify identity for which group. So I write EG and EH. So it makes sense that I need this one to be identity and this one to be identity, right? If I get identity on one and not identity on the other, it doesn't work. And if you think about it, if this, you take the order of G and order of H and you take the LCM, right? So this is LCM of order of G and order of H. Yeah, so the order of elements in our group here is very explicit. So an example, would be Z2 cross Z2, right? If or some people write it like this, right? So the elements are clear, right? They're remainders when dividing by 2. These are the elements, right? And then you have something called, I don't know if the book names it, but it's called Chinese remainder theorem. So Z mod MZ. So you might wonder, right, what happens when I take direct product? I mean, exterior product. And it turns out it's actually isomorphic to this. If GCD of M, I think it's if and only if, of Mn is 1, right? So if they're co-prime, they're isomorphic to just that cyclic group, right? So for example, Z mod 3Z cross Z mod 5Z is isomorphic to Z mod 15Z because 3 and 5 are co-prime. But in the not example, right, So Z mod 2Z, the example I have above, this is not isomorphic to Z mod 4Z. Yeah, because 2 and 2 are not coprime. And you can see this, right? So question for right here, the order of 0 is 1, right? In Z mod 4Z. Order of 1 is 4, right? It generates the whole group because it's, you know, 1 plus 1 is 2, 1 plus 1 plus 1 is 3, 1 plus 1 plus 1 is 0, right? The order of 2 is 2, right? And the order of 3 you could check is 4, yeah? So here on the other hand, the order of 0, 0 is 1 because it's the identity. The order of 1, 0 is 2 because 1 plus 1 is 0 and 0 plus 0 is 0. The order of 0, 1 is 2 and the order of 1, 1 is 2, right? So you see these groups can't be the same, that their elements don't even, their orders don't even match, right? So, and it's exactly the problem, the thing here, right? The LCM thing, right? The group on the left-hand side is not cyclic. You have no elements of order 4, right? No element generates the whole group. Okay, any questions so far? Okay, so internal direct products. So this is the opposite. So given a big group, decompose to product of smaller ones. So basically, I want to write G as, something like HK, where HK is the set of HK, H and H, K and K, right? So what it means is G equals HK, H intersect K is E, and HK is KH for all K and K, H and H. Yes, and then so if these properties are satisfied, then G is internal product of H and K. So question, why is part 3 important? Why do we need sort of like this abelian property between H and K? So question, is HK a subgroup, right? I mean, if HK is not a subgroup, I mean, is HK a group, right? Or forget, whether it's a subgroup of G or not. Is it even a group, right? If I take H1, K1, and I group operation, H2, K2, this better be an HK, right? Or a group, if I take 2 elements in a group and I do the group operation, it has to remain in the group, right? So what does it mean to be in here? Well, it has to be by definition, right? What's HK? It's elements of the form, of something in H times something in K, right? So it better be something like H3, K3, right? For some. H3 and H, K3 and K. But you see, it's actually pretty hard here, right? Because you don't know if an element here is of this form, right? So it might not lie in HK, but if you have part 3, then I could swap these two, H1, H2, K1, K2. Now, this is an H, right? This is an H. So since H is a subgroup, H1 H2 is an H. So we call this thing our H3, right? And then this is in K, this is in K. So we call this like our K3, right? So it's true if you could swap, right? But in general, like you might not be able to swap. Everyone clear so far? So like on your homework, I think on your homework, I think they say G order of G is 20, right? You have element order 4 and element order 5. So the fact that they and they tell you they commute, right? They tell you they commute. So the fact that it's the intersection is E, that should be easy, right? I mean, again, you have order 4 and order 5. If something is belongs to both of them by Lagrange, you must divide 4. The order must divide 4, and the order must divide 5. Not many numbers are factors of 4 and factors of 5 except 1. So the fact that intersection, so you just need to check that G is HK. And to do that, just prove, right, if you have this element, let's call it G, right, it's order 4, and you have an element H, order is 5, then prove, G to the I, H to the J are all distinct, right? For I less than or equal to, between 0 and 3, J between 0 and 4, right? And basically I'm saying because the order is 4, so you have E, G, G squared, G cubed, right? That's your set. It's order 4. And then you have H, H squared, H cubed, H to the 4th. So take products of each, right? Take, so I get like E, EH, in this case, it's stupid to write E, but, and then you do product with G, right? G, GH, GH squared, GH cubed, GH to the 4th, right? They're all distinct elements, right? Because the order, right? By definition of order, all these elements are distinct, right? And then how many do you have? Well, you have 20 already. So there's like 20 of these, and your group's order 20. So it must be so you see it must be G is equal to HK, right? So you prove it by just consider HK and show that it's already 20 elements. So, okay, moving on. Any questions so far? Hopefully, I'm not going too fast. Okay. So recall cosets, right? G mod n, G to n is number of distinct, I guess let's call it left cosets of n in G, right? I forgot the English word for that, but it's like something like this, right? So we define a subgroup H of a group G is normal. That's normal. Normal if and only if GH is HG. And if you multiply by G inverse on the right, this is the same as some books write it like this, right? So again, what does this mean? It means that GH1 G inverse is equal to H2 for sum. Right, so the H1 and H2 could be different, right? Because that's what capital H means, right? You don't have to be the same element. The element don't have to be the same, right? That element just has to lie in H. So examples would be, abelian groups for abelian groups, all subgroups are normal. So this is for all G and G, right? So G is the bigger group, right? So it means, if you want to think about it, if I conjugate by G, I remain H, yeah? If I conjugate every element in H by G, I still get elements in H. So why is this the case? Well, this is easy, because since I commute, this is true. It's not hard. Yeah? So because it's abelian, things commute, so I could move the G inverse past every element of H, and then I'm done. So abelian groups, every subgroup's normal. Now remember, G mod n is what? It's the it's the number of cosets, or the output left cosets, right? And this form a group if n is normal. So I'll suggest you read book, or you try proving it yourself. Read book to see what fails if n is not normal. So you could think of normal as two ways, right? Either left coset is equal to right coset, or when you conjugate, you remain the same. Yeah. So I'll leave it there. And the operation is clear, right? Operation G1n, G2n. We define this to be G1, G2n. Yeah. And clearly the order is, the order of this group is the index, right? We defined this last time. Is everyone clear? So again, be careful. So we normally write G mod n as like, an example would be G is Z and N is 3Z, right? So G mod N in that case is just remainder is mod 3, right? So G equals Z, H, or N, if you like capital N. We normally use N, yeah, if the group is normal. Yeah, so N is for normal, yeah. So when you write N, group theorists tend to think immediately that like it's a normal subgroup. So in this case, right, N is normal because G is abelian, right? I mean, integers are abelian, right? Like 1 plus 2 is 2 plus 1. And then G mod N is exactly what you think. Write it out, right? This is remainders mod 3, right? Mod 3. Right, so if you if the group is not normal, like G mod N, like it still makes sense as a set, right? As a set, it's just the left and right coset. So G mod N is still a set. But it doesn't form a group. If n not normal. Yeah, so I mean, normal only makes it a group, yeah. G mod N still perfectly makes sense as like sets, right? I mean, it's the set of elements given by like this. So, but like in order to define a group operation and to make it a group, then, you need normality. So any questions so far? Are you all clear? Very silent today. Uh, since we got score yesterday, wait, score for what? The oh, I see. Okay, so let me just talk about the homework, the commutator subgroup, and call it a day. Yeah. So so let me just the commutator subgroup. It's the group generated by elements of this form, right? A, B, A inverse, B inverse for all A, B, and G. Yeah. So I will leave it to you to check. Leave it to you to check. It's a subgroup. Yeah. So you need to check this thing as a subgroup. Yeah. Like it's closed under. Has inverses. Blah blah blah. Yeah. So the normality is easy. So the group generated. So commutator is normal, right? So I need to check again. Let's go back to what normal means. I'm going to use this definition. Yeah. So let G be in G. Do I want to use G? Let H be in G. Yeah. And G be an element of commutator subgroup. So let's assume you prove that it's a subgroup. Yeah. So I need to show H inverse is G1, right? For G1 in commutator. The reason I write this is because I don't know I believe there's a letter they use for it. So I don't want to write H yet. So I think some books might use another letter. So I'm just gonna write in commutator subgroup. So this is easy. So what we're gonna do is we're gonna multiply by E, but in a very smart way. We do G inverse G. Now you're done because this element is by definition in commutator, right? Because remember, what does commutator mean? Commutator is elements of the form A, B, A inverse, B inverse, right? And here I have H, G, H inverse, G inverse. So this thing is in commutator by definition. And this one we assumed was in commutator, right? G and G be an element of the commutator. And if you proved it's a subgroup, right? This is in commutator, this is in commutator. A subgroup is closed under group operation. So this is in commutator. Yeah. Everyone clear? So that part is easy. If you once you prove that it's a subgroup, so I'll leave that to you. So one last thing, the second part says show G mod n is abelian. Right. So remember G mod n, if and only if n contained in commutator. Subgroup. So let me explain the idea. Yeah, I'll let you write the whole proof. Like, I mean, it's your homework. But the idea is, I mean, first off, right here, it's a abelian. That G mod n is a abelian group means what? means in particular it's a group, right? So n better be normal. And it's normal because in the first, commutator is normal. So the first thing you have to show is if you're contained in a normal subgroup, it's your, let me just go back. Yeah, oh, sorry, that's not true. So n is normal. N normal subgroup. Now that I think about it, it's not true. So in practice, it's a group already. So this part you don't need to show because n is normal. So you just need to show it's abelian, right? And let me ask you a question here. When I quotient off by 3z here, what am I doing? What am I claiming right now? I'm claiming everything in 3z is what? Is 0, right? I'm basically claiming, if you think about it, every multiple of 3 is just 0, right? In Z mod 3Z, like 3, 6, 9. And that's because, remember, when you quotient off by n is the identity, right? It's En, right? So, and in integer sense, the identity is 0. So you see here, basically everything in what you quotient out by, in this case 3z, it becomes identity, right? So when you quotient G mod n, right? N is identity, right? It makes sense, right? Because the operation is given by this, right? So En times G1n is G1 is by, if we follow this notation, it's E G1n, which is G1n, right? So N is clearly the identity, right? So basically we make N the identity. Now, if you quotient off by the commutator, right? I'm making the commutator the identity, right? If I quotient off commutator, I hope I'm spelling this right, of commutator, I'm making it identity, right? And same for anything belonging to the commutator. But what's the commutator? Commutator is this, right? So AB, A inverse, B inverse. This becomes identity. And now you see what's happening, right? If I multiply by B, what do I get? I get AB, A inverse equals B. And now let's multiply by A on both sides. I get AB is BA. Yeah. And this is exactly a abelian property. So that's the idea. Yeah. I mean, of course, you need n's here, right? Capital N's, because it's on the level of cosets. But this is the idea, right? If you quotient off by anything in the commutator or a subgroup of the commutator, everything, it becomes abelian by definition because you're setting it to be identity. Yeah. So I'll just write idea. Notation is not correct because we're working with cosets, but everyone good. I think those are like the two hardest problems on the homework. So just giving him. Yeah, let's call it a day.